So what we do is we go back, we take the power series work we did in 9.2 and we go back and apply that to the Taylor series that we introduced in 9.1. So what was a Taylor series again? Taylor series, well, I should say a Taylor polynomial was a polynomial approximation of a function. So we had a Taylor, consider we have a Taylor polynomial, and we connect that with the idea of a power series. And the way we connect these, since a power series is an infinite degree polynomial, and a Taylor polynomial was typically of nth order, was an nth degree polynomial based on the derivatives of a function that we created in order to approximate the function better and better near some center value a. Well, if we put those together, we get a Taylor series. And to do that, you just let the Taylor polynomial, instead of being nth order, you let n go to infinity and you have an infinite degree polynomial, but you get it by creating the terms of the polynomial based on the derivatives of a function. So this is put together with the definition, and it's actually on the next page. Taylor series. So we had a formula for a Taylor series. For a function f centered at a, and again, centered at a means you can think of that as the point of tangency that we had before in the Taylor polynomial. And so you started by the constant value being the value of the function at a. Then you took the derivative of the function at a and multiplied that by x minus a. Then you took the second derivative of the function at a and divided by the 2 factorial and did x minus a squared. And we would keep doing that until we got to the nth degree. But in this case, we're just going to keep doing it. And if we just keep doing it, then instead of getting an nth order Taylor polynomial, we get a power series, which we call the Taylor series. So we can write this with a formula. So this is equal to the summation as k goes from 0 to infinity. And again, you take the kth derivative of the function and divide it by k factorial. That's why these factorials show up, and multiply that by x minus a to the k power. So we already looked at this as a way to create a linear approximation to a function, a quadratic approximation to a function, a third degree approximation to a function, etc. when we were in 9.1. And we saw that the farther you went down and the better you got the polynomial to agree with the function in rate of change, in curvature, in rate of change of curvature, etc. That as you went to a higher degree and took a higher order derivative and made everything match up, you got a Taylor polynomial that had a better and better agreement with the original function. It really often still only agreed at a. There was a point of tangency, but it got closer and closer the farther you went out. So we can kind of ask ourselves what happens if you just go off to infinity. If you let the agreement of your Taylor polynomial become infinite. And the idea is that as long as the series that you get converges, then you actually get a polynomial version of the function. That it no longer is an approximation, they're actually equal. Now, most of the examples we usually like to look at, because they just make it a little simpler, are when a is equal to 0. We centered it at 0. We already did that for sine of x. We did that for e to the x. And we'll look at those examples again. But now this time we'll extend them. However, because that's a very common thing to do, that gets a special name. So if a
Actions allows us back to the project family package of
if x is equal, if a is equal to 0, so meaning that we're centered at 0, we call this the Maclaurin series. So again, it's just, somebody's, name. So the Maclaurin series is just the Taylor series centered at 0. And this is in the definition box on page 6. It's in this definition box on page 685. But let's remind ourselves what this looks at. Let's do an example. This is their example 1 for the section. And they have a couple of them, but let's do, this is A, let's let f of x equal cosine x. So we did sine x as an example graphically, and I pulled up the graphing calculator and we looked at it, how the second order Taylor polynomial was an approximation for sine x and things like that. So this time let's look at cosine x. But this time we're not going to stop with a quadratic approximation or a third degree approximation. We're going to do an nth degree approximation and see what happens. And that's going to be the Taylor series. So again, you can just follow the formula. So to follow the formula, we have to look at the derivatives. So let's look at the instructions. It says, find the Maclaurin series for the following functions. Find the interval of convergence. So this means we're letting a equal to 0, and we're going to use the Taylor series formula. And so f of 0 equals cosine 0, which is 1. F prime of 0. I'm taking derivatives because in the formula, we have to find these coefficients which involve the derivatives of the function. So I'm finding the derivatives of the cosine function. So the derivative of cosine is minus sine. So that would be minus sine of 0. But sine of 0 is 0. The second derivative, the derivative of minus sine, is minus cosine, which we're evaluating at 0. So that would be -1. The derivative of that, derivative of minus cosine, is sine. And again, we're still evaluating it at 0, so we get a 0. And then the derivative of sine takes us back to cosine. I'm out of space. So basically we have a pattern here that we have 1, 0, -1, 0. We have this pattern. So let me transfer that over here. We have 1, 0, -1, 0. All right, so if I'm trying to do the power series, then we're going to have the Maclaurin series is the summation as k goes from 0 to infinity. And we have the kth derivative evaluated at 0, and we know that that produces this sequence of 1, 0, -1, 0. Divided by k factorial times x to the k. And I don't have a minus a because a is equal to 0. So what does this look like? Okay, so when k is 0, I have a 1 here, I have a 1 here, and so I have the derivative is just the function at 0, so this starts with a 1. So then when I take that's sort of taking the 0th derivative. So when that's this first part here, cosine of 1. So I'm going to try to check these off. So that's this one. So now when I take the first derivative of cosine, I get minus sine. Then when I plug in a 0, I get a 0. That's the second term there. So that means this whole coefficient is a 0, and so I get a 0 in my next term. Then when k becomes a 2, then I'm down to this one down here, so that the function's derivative the second time evaluated at 0 is -1. So I have -1 divided by 2 factorial times x squared. Then when I get to the third derivative, then I'm down to here where I get a 0 again, so I don't really care about the rest, I get a 0. Then when I get the fourth derivative, I go back to where I started and I'm back to where the 1 is. So that means the top of my fraction is a 1 over 4 factorial times x to the 4th, etc. So if I take out the 0 terms and look at the pattern here, then the Maclaurin series for cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc. So it is sort of formulaic, but to use the formula, you have to take derivatives of the function and evaluate at the a value, which hopefully will be 0 most of the time, because that just makes it a little bit easier. Okay, so now we're also supposed to try to find out the radius and the interval of convergence of this series. So what I'm going to do is I'm going to bring the series to the top of the page as our result. Okay, so we have 1. Well, I think we actually started with a minus. There we go. X squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial, etc. So this is a series. And so we can sort of ask ourselves, when does this converge or when does this diverge? And so in order to do that, we have to figure out how could I apply a test to this? This is an alternating series. So I would be looking possibly to apply a test like the way we did before. What we did last time is we used the ratio test for the absolute value of the terms to try to see where it would converge absolutely, which would lead to regular convergence. Again, all chapter 8 stuff, which you may or may not have gotten comfortable with yet. So to use the ratio test, I need a formula for these. So I need to write this as a formula. So I have k going from 0 to infinity. So my coefficients are alternating in sign. So there's a -1 there. Remember, you may recall we did this when we had alternating series. And when k is a 0, it's not there. So this is sort of my first term, my second term, my third term, my fourth term. So when k is the odd numbers, it's positive. And when k is even numbers in my series, it's negative. Well, actually, I should say the 0th term. Let me index my case correct. This is a 0. This is 1. This is 2. This is 3, because I want to start at 0. Or I could start at 1. Anyway, either way, we want to do this. The notation doesn't matter as long as it makes it come out correct. So now the even powers are positive, so I'm just going to put a k up here, because then an even exponent on -1 will give me a +1 when it should. Then what am I dividing by? So I'm not dividing by the number factorial. This is a 1. Let's fix that so it's legible. So I'm dividing by the factorial of twice the number. So I'm going to write this as 2 times k factorial. And similarly, I'm then raising x to the power that's twice the number of the position that we're in, 2k. So I'm writing a formula for this particular Taylor series, because then I can do things like apply tests. Like in this case, because we have a factorial, we're going to apply the ratio test to try to see where does this converge or diverge. So to do the ratio test, I would take the limit as k goes to infinity of the k plus 1th term, but with absolute value. So I'm going to put absolute value so that we're looking for absolute convergence. And that means I can ignore this part, because the absolute value of -1 to the power is always just going to be a 1. I can ignore that. So then what do I get? I get the k plus 1th term. So that's x raised to the power of 2 times k plus 1. Because I'm replacing k with k plus 1 divided by 2 times k plus 1 factorial. So this is the k plus 1th term, where I took out the -1 because I'm taking the absolute value. And then I would divide this by the kth term, which means I'm going to take the reciprocal and multiply. So that's going to be 2k factorial divided by x to the 2k. I take the limit of this as k goes to infinity, and x is a constant compared to k, so I can pull it out. It's an absolute value. And when this is less than 1, this converges, and when this is greater than 1, this diverges. Okay, so we get to do some simplification here. Maybe that's a little hard to see, so let's take a step to do this. Again, the book will help you with this as well. So the power here, if I distribute, is 2k plus 2. And this is 2k plus 2. So this is the limit of absolute value of x to the 2k plus 2 divided by x to the 2k, and 2k factorial divided by. And if I have 2k plus 2 factorial, again, the way the factorials work is you start with the number and you multiply your way down. So 2k plus 2 factorial, if I put that down here, would be 2k plus 2 times 2k plus 1 times 2k counting down, which means 2k factorial. So I'm pulling off the first two multiples because then I can see that the top and the bottom of the fraction on the right both have 2k factorial, and I can simplify. So how is this going to simplify? This is going to cancel with that. And if I take x to the 2k plus 2 and divide it by x to the 2k, when you combine exponents, you subtract. So this would be minus 2k. So those would cancel. So I'm left with the limit as k goes to infinity of the absolute value. So in this case, this went away, and I just have x squared on the top. And in the bottom, I have 2k plus 2 times 2k plus 1. So for any number of x that I plug in here, I get that number squared on the top. Like let's say I plug in 1,000. So on the top, I'd get 1,000 squared, which is 1,000,000. But whatever number I get there, I let k go to infinity. The denominator is heading toward infinity while the numerator is not. So this limit is 0 for all x values. So that means by the ratio test, we get this converges for all x. So that means that the Taylor series for cosine x, the Maclaurin series, because it's centered at 0, is infinitely accurate of an approximation, meaning that it's off by nothing. So literally, cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial for every value of x. That means that this infinite polynomial that we come up with using the Maclaurin series, the Taylor series centered at 0, that is cosine x. So cosine x is this polynomial. They're the same thing. Questions, comments, discussion? So we just expressed a trigonometric function as a polynomial. We don't normally think of those in the same classification. And they're still really not, because all of our work with polynomials have only been with finite degree polynomials. We've only just introduced the idea that a polynomial could just have powers that keep going off to infinity. And we certainly didn't really think about that something as normally that would converge very often. But this converges for all values of x. So that means it doesn't matter what you plug in for x. This series is going to converge, and it's going to settle on a value of cosine of that number. That this polynomial is a periodic function with a period of 2 pi. So this just is kind of like a real head scratcher for most students. It took a lot to get here. It's kind of hard to understand. But this is the quintessential idea of what Taylor series do for us. They give us an ability to express transcendental functions, non-algebraic functions, as polynomials. As long as the function is differentiable and you can get derivatives, and as long as the series converges, that if you allow this infinite Taylor series to converge, then you get another way to get the values of this function. And basically, this is how calculators work. Like, how does the calculator come up with cosine x? Well, they have this polynomial. They plug in a polynomial and they go far enough out in the degree terms of the polynomial to make sure that the decimal is accurate to the end of the decimals on the screen of your calculator. So this is sort of the nuts and bolts of how a calculator finds cosine for you. So we can try to convince ourselves of this and understand this a little bit better. So take a look at the polynomial and let's think about it for a second. For one example, if I plug in a 0 into this polynomial, I get a 1. And if I plug 0 into cosine, I get a 1. Notice that the cosine function is an even function, meaning it's symmetric with respect to the y-axis. Well, notice that the polynomial is even because it's only made up of even powers of x. So if you plug in a positive or a negative value for x, you get the exact same thing, just like any normal even function. X squared is an even function. X to the fourth is an even function. Any sum or difference of x squared and x to the fourth is an even function. So because these are even terms, even powered terms, that's an even function. Okay, well, imagine this. What if I take the derivative with respect to x? Well, what's the derivative of cosine? Minus sine. Well, we did a polynomial approximation, a Taylor sort of second order Taylor polynomial approximation for sine. And we got stuff kind of like this, but with odd powers. So if I take the derivative of this, what happens? Well, the derivative of 1 is 0. The derivative of x squared over 2 factorial is just 2, but I take out a 2 and that multiplies out and I get minus x. If I take the derivative of the next one, I get 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial. And if I multiply both sides by -1 so that I get the sine function, I get that sine of x is equal to positive x. And notice that 4 cancels with the 4 in the 4 factorial, leaving you with 3 factorial. So I get minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So that is the Taylor series for sine. I'm using the theorem we had in the last section where when you have series, you can differentiate both sides and get another series. But in this case, I differentiate cosine and I get sine. Well, I get minus sine, and then I adjusted that to give me sine by multiplying by -1. Now imagine that I took this sine and I took the derivative of that. Well, guess what? You get that. The derivative of x is 1. The derivative of minus x cubed over 3 factorial is minus x squared over 2 factorial. You can literally see when these are written as polynomials and you differentiate term by term, why the derivative of sine is cosine. We looked at that numerically before. We said we can't really do it any way other than numerically. Well, now we can actually do it term by term when they're written as a polynomial. So they've thrown a couple things we won't have time to look at that are much less critical, but still something you guys should look at. See if you have questions on, like the binomial coefficients. You guys are going to hate that. But I want to finish up in our last few minutes by looking at the table as a summary of their results, because you're going to want to come back to this table a lot. So as you can see, by using the Taylor series formula or the Maclaurin series, you can come up with the Taylor series for sine and for cosine. And we already know for 1 over 1 minus x, because that was the geometric series result, and that worked for certain things. We did a Taylor approximation before for e to the x. So they let that go off to infinity, and they accumulate some results basically. So let's finish up by taking a quick look on page 694. This is right before the exercise set at the end of 9.3. They have table, and you guys are I'm gonna just draw your attention to this as much as I can. 9.5. Use it. Think about it. This is the end result, basically, from these first few sections. There's one more section in 9.4, which we'll look at next week. But that basically is just sort of working with Taylor series, just thinking about all the different ways we can work with them by differentiating them to get new ones and using them to approximate function values by going out to the 5th degree in the Taylor series or something like that. So on the table, we have a big list of results, and they list out the function, what the series is, what the formula for the series is, and what the domain of the series is. So for example, it has 1 over 1 minus x, which we were looking at, and they point out that's 1 plus x squared plus x cubed, etc., because this is just a geometric series, and that you can write that as a formula where you have k going from 0 to infinity of just x to the k. So this is our simplest polynomial, and this works when the absolute value of x is less than 1. So this is one of our results. Well, imagine that in every one of these x's, I could plug in like an opposite of x. I could plug in a negative x. And if I replace x with the opposite of x, I get 1 over 1 plus x. And if I put in a minus of x here, all the odd power terms would become negative. So then I would get 1 minus x plus x squared minus x cubed plus etc. And this could be written as a summation as k goes from 0 to infinity. And I would like throw in the -1 And that would be k times x to the k. And this would still work when the absolute value of x is less than 1 because we just substituted in. That was using the composition rule in that theorem back there. You can plug in a function for x. And last one to look at, and then I know we're out of time, e to the x. We did a couple of terms of this, but if you do it all together, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. It's actually really simple for e to the x. And that's the summation formulaically from 0 to where you just have x to the k divided by k factorial. And we already saw with this that this converges for anything. So this is absolute value of x basically just being less than infinity. So this is a polynomial for e to the x. And take note, if I differentiate this term by term, I get the exact same polynomial. That's why the derivative of e to the x is e to the x. Because when I differentiate this polynomial, it doesn't change. And they go down. There's a total of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. See all 11 of the table. Okay, so that's where we're going to stop today, focusing on drawing your attention to this table, trying to wrap your mind around that. So let me stop the share, stop the recording.